Hi guys, there was another question from section 5.4. This I believe was the last homework assignment on this section is number 213. Okay, so we are again asked to use the limit comparison test to decide if this series converges or diverges. We have series n to 1 to infinity of 1 over e to the power of 1.1 times n minus 3 to the n. Okay, so the idea, of course, is one thing that I'll always like to do is look at the dominating term. I'm sure if you're wondering why would they put 1.1, why did they put 1.1? Because if you actually rewrite this as e to the 1.1 and then all that raised to n, you do notice that actually this number, e to the 1.1, I'm just going to put it right here, e to the 1.1 is actually approximately 3.0042, and of course it goes continuous, but so you can see that actually that e to the 1.1, which sort of like become your base here, it is larger than 3. So that kind of would be your dominating term because this has a bigger base. Not by much, but still bigger. So then the motivation would be to compare this to the series. And by the way, this is a geometric series. I think a couple of pages back, I don't know if it was this section or last section, you did learn about geometric series. And of course, if you compare to, and again, because that is a dominant term, we're going to use the same term, except now why is this geometric series? Because you can rewrite this as 1 over e to the 1.1 and then the quantity to the n. Because as you can see, if you raise 1 to the n, of course, you're still going to get 1. Also, that to the n becomes the same thing. And of course, this is your radius. I should say not radius, but ratio. So this is your little r in geometric series. Of course, as you remember, if this is less than 1, which obviously 1 over e to the 1.1 is less than 1, so that geometric series converges, right? So we do have a convergent geometric series. So the motivation will be try to compare this to that. I just want to make sure I remind you that why this is a geometric series and also why does it converge, because again, your r, in this case, your ratio is less than, in absolute value, is less than 1. Of course, it's positive, so you don't need the absolute value, but it is less than 1 because this is, of course, bottom is more than 1, okay? Anyway, so we're going to compare to this series and see if we can get a limit. So we're going to look at the limit as n goes to infinity of, so this is going to be our nth term of the series, 1 over e to the 1.1 times n minus to the n, and of course all over 1 over e to the 1.1 times n, which is what we decided was the nth term of a geometric series. So as you reciprocate this, multiply by top, this becomes the limit as n approaches infinity of, so this goes on top, that becomes e to the 1.1 n, and then of course all over e to the 1.1 times n minus 3 to the n. So really actually quickly, there is something called leading term approach. Whenever you, this of course only applies when n goes to infinity. You can actually take the leading term with the top over leading to the bottom. So really you can quickly see the limit is going to be 1 because this is the leading term again on the bottom. Remember, because the base here is going to be, if you rewrite e to the 1.1 times n as e to the 1.1 quantity to the n, so that number, as I said, was more than, bigger than 3. So that's one way to see why this limit is going to be 1. Now you can also take top and the bottom and divide it by, again, the leading term, which will be e to the 1.1 n. So as you do that, because sometime when n goes to infinity, you can actually take that approach, or you can just take the leading term. But either way, you should get that at the end of the day, this will be the limit as n goes to infinity. So if you divide everything by the leading term, so on the top, you're just going to have e to the 1.1 n over e to the 1.1 n. And then the bottom, we're going to do again, same thing. Take every term divided by the leading term, which is e to the 1.1 times n over e to the 1.1 times n. And then minus 3 to the n over e to the 1.1 times n. I'm sure you remember this approach from probably calculus 1. Anytime you take the limit as n goes to infinity, you can take every term in your expression divided by the leading term. Now in this case, the leading term, of course, would be e to the 1.1 n, because remember that e to the 1.1, the base was bigger than 3. So as you reduce this, let me see if I can move it up here. So as you reduce that, well, the top becomes 1. So this becomes, I'm just going to move it over here, this becomes the limit. So we're going to move it from here up here. This becomes the limit as n goes to infinity. So again, that's going to be 1 on the top. This is also going to be 1. Now remember, 3 to the n over e to the, I can rewrite that as 3 over e to the 1.1, and then the whole thing to the n. That's just a little algebra here, because as you take top to the n becomes that, and of course bottom to the n becomes that. So we just rewrote it. Now why is that important? Because as n goes to infinity, remember this is a base of your expression. Of course this base is less than 1. Now why is it less than 1? Because remember e to the 1.1 is 3 point something. So because the bottom is larger than top, so this your base is less than 1. Now anytime you raise a number less than 1 to bigger and bigger power, of course it goes to 0. So this term goes to 0, and of course all you have is 1 over 1, which becomes 1. So I'm just going to say, because that limit becomes 1, the conclusion of course would be our series, or the series, converges by, and this is important too, because remember there are 3 parts to limit comparison test, by part 1. If you go back and look at the part 1 of the limit comparison test. Okay, it says that if that limit is a positive number, as long as the bottom series converges, so does the top. So remember, once we got the ratio, since the bottom was a convergent geometric series and our limit is positive, that means our series itself converges. Okay, I hope that helps.